To follow up on our discussion that we had regarding how the derivative and the first derivative and the second derivative connect to the graph of a function, let's do a few examples where we want to find all of the critical points for a given function. And let's use this number 5 here, y equals cubed root of y equals x cubed minus 4x. And so then let's take the first derivative of that, which would be 3x squared minus 4. And then let's also take the second derivative of that, which would be 6x. And let's take a look then at finding all of the critical points. Remember, for our critical points, we might have maximums, minimums, or points of inflection. And those points start to occur when the first derivative equals 0. That means we have a critical point, and when the second derivative equals 0, so this identifies your critical points, where the second derivative equals 0, we have a point of inflection. So let's go down here and take the first derivative and set it equal to 0. And when we do, we get 3x squared equals 4, x squared equals 4/3, or x equals plus or minus the square root of 4/3. And we can take the square root of 4, so it would be x equals plus or minus 2 over the square root of 3. Now that equals approximately plus or minus 1.15, but the exact answer is 2 over the square root of 3, or we could rationalize that to say 2 square roots of 3 over 3. So what we know is at x equals 2 over the square root of 3, and at x equals negative 2 over the square root of 3, we have critical points. So we have just found the location of 2 critical points. Now what we need to figure out is what is happening at those critical points. If our graph is a graph that is concave down, then that means we have a maximum critical point. If our graph is a graph of concave up, then we have a minimum point, and if the at that point it is a point of inflection, that's when our second derivative would be 0. So remember that the second derivative equal to 0 gives a point of inflection, but otherwise it tells us whether we're concave up or concave down. So let's take the second derivative and plug in 1.15, and take the second derivative and plug in negative 1.15 and see what we get. Well, I'm multiplying the first one by 6, and I'm multiplying or both of them by 6, because the second derivative is 6x. So whatever I get when I plug that in, it doesn't matter. I'm going to get a positive answer. And if I get a positive answer, that means my graph is concave up, which means I have a minimum as a critical point. And likewise, if I am plug in a negative, I'm going to get a negative answer, which means I'm concave down, which means I have a max. And so now the other question is, well, do I have a point of inflection? Most likely I've got to have one, because if I change concavity, the point of inflection is where I change concavity. So since I didn't get a point of inflection here, then what I've got to do is take my second derivative, 6x, set it equal to 0, and that tells me at x equals 0 we have a point of inflection. And then the only other thing we may want to do is to find the corresponding y values of each of these points. So we know we have a critical point at 1.15, negative 1.15, and at 0. And to find the y values, we're going to plug it into the y equals x cubed minus 4x, the easy one. When I plug in 0, I get 0. When I plug in 1.15, I get negative 3.1. Now remember that these are going to be estimates. I'm sorry, I have that backwards. When I plug in negative 1.15, I'm going to get, no, I do have that right. And when I plug in negative 1.15, I'm going to get 3.079 or 3.1. Okay, and those are just estimates. So let's look at what the graph looks like here. I have a critical point at positive 1.15 and negative 3.1, so somewhere down there, and that is going to be my minimum. And then at negative 1.15, I have a critical point up here at 3.1. And I have a point of inflection at 0, 0. So when I draw this sketch, I know that the maximum is there, the minimum is there, and where I go from being concave up to concave down is right at 0, 0. The other points that I certainly could have found would have been by taking x cubed minus 4x, setting it equal to 0, and I would have found the addresses of my x-intercepts. And all of these points are valuable points when we're talking about a company. I don't really, as a business consultant, I don't really care necessarily what the graph looks like, though the graph is very telling. But if I know that a company is concave up, then I know they're going to hit a low spot in their career, and then they're going to continue to improve. But if a company is concave down, then I need to worry because they're going to max out and then they're going to start falling. Likewise, the point of inflection actually indicates more about the change of a company than the max or min. The max and mins are important, but the point of inflection is when you see a shift change, where we go from either doing really well to starting to level off, or going from just making it happen to really taking off. So the point of inflection is an important point. So as we start to go through some business applications, you'll see that these all of these things tie together, and it's important to be able to find all of them. Now let's take a look at this number 6, the function f of x equals 2 to the x. That is an exponential function, so it looks quite a bit different than other graphs that we see. Let's take the first derivative. The first derivative of an exponential is the ln of the base times the original function. And the second derivative, oops, I didn't mean to do that, equals, the ln of 2 is simply a coefficient, so we're going to just write that. Now we're going to take the derivative of 2 to the x, which is the ln of 2 times the original function 2 to the x. And so if we clean that up, we get the ln of 2 squared, not the ln of 4, times 2 to the x. Now we don't even really have to do a lot of plugging in here. We just need to do some thinking. 2 to the x is a function whose values are always positive, because if you take 2 to any power, you're going to always get a positive number. In terms of the first derivative, The ln of 2 is a positive number, and 2 to the x is a positive number. So this is going to always be positive, which means the function is going to be increasing. And the second derivative, again, is always positive, which means that it is always concave up. And what that means to me as a business consultant is that this company is going to continue to improve. So if you remember anything about graphing exponentials, the exponential always goes through the point 0, 1, because anything to the 0 power is 1. And this is an increasing function that never crosses the x-axis, and it grows what we call exponentially as x gets bigger and bigger. Notice that it's always concave up and it's always increasing. So this is a good company to invest in. The example we just did before, that company's going to have some ups and downs, but this company has a solid plan and its investments are going to continue to pay off. So again, making that connection between what the derivative tells us. Could we just look at the graph on a calculator? Absolutely. Do we need to know that it's called concave up or concave down in the business world? Maybe, maybe not. But understanding that and where it comes from also allows you to take models and determine just from the model whether this company is doing well. So it's all tied together and you can look at it in bits and pieces. We're getting ready to do some applications of businesses, and as we do that, always use your graph and the information you know about it to help you make decisions.